Hello, good evening, students. Welcome to another class of Vedantu Karnataka. This is Catherine, your physics master teacher. Students, quickly, can you let me know if I'm live, audible, and visible? How are you all? Are you all doing well? Let me also check if I'm live. Yes. Hi, Sanjana. Hi, Harihar. So, can you quickly send this link to your friends and say today is the last class where we're going to finish chapter 1. Okay, so we have been doing a series where we have already two videos with the first two parts. Today we'll finish off Gauss Law, and that's the end of chapter 1. Hi, Kirti. Hi, Savio. Okay, so we'll start in 1 minute. Yes. Are you all ready to learn Gauss Law? Yes. Students, if you're looking for offline classes at Vedantu, we have our new center in Bangalore, which is for all of you. It is at JP Nagar. So please do visit the center and check out if you want offline classes. Okay, let's start. So in the last class, we discussed till this one, dipoles. Okay, so those of you who have not watched that, you can just go watch the previous video, which is dipoles. So today we're going to start with continuous charge distribution. So for students who are wondering what is happening here, we are looking at chapter 1 of electrostatics from the NCERT. Okay? Yes. Okay, so let's start. So continuous charge distribution. So what is continuous charge distribution? So you might have charges at random places. So imagine you have a charge here, I have another charge here, I have another charge here. So these are all different charges at different points. But imagine I have charges everywhere. From here to here, I have charges continuously. So that's when you can say charge is continuously distributed. Okay? Let me take my eraser. Okay. Yeah. So in all these chapters, we've looked at charges. We've been dealing with charges for like last two classes. Okay. Now, here we're looking at charges over specific areas. For example, let's say you have a sheet. Okay. Let's say you have a sheet. Okay. And there are so many charges on this sheet. This sheet is full of charges. Whatever charge you want to put, you can put it. Okay. It's full of it's full of charges, and the sheet has what alphabet do you want? The sheet has an area. Let's put it as A. Okay? And then let's say each of this charge is Q. So what will Q by A be now? Q by A will be the area charge density, which is the amount of charges in a particular area. So this is going to be equal to sigma or area charge density. Okay, and what would its unit be? Its unit would be unit of charge is coulomb. So coulomb per unit of area would be meter square. Okay, now you can actually consider so many different shapes. So according to our NCERT, let's consider the shapes that are given in our NCERT. Let's take the next shape. I'll use yellow color. Okay, so for the next shape, let me draw a cylinder. Okay. So imagine this is a wire. It's a little thick, but imagine this is a wire. Okay. And there are so many charges inside the wire. I have a cold, students, so my sound would be a little different. I'm really sorry. Okay. So this is a straight wire. And then let's take a small area. Okay, this color doesn't look good. Let's take a different color. Which color? Blue. Okay, let's take a small area on the wire. Let the length of this part, this small area be d, and the charges q itself. Now, if I do q by d, oh, can you see? Yeah. If I do q by d, and I say it is equal to some lambda, what will this be? This will be linear charge density. Okay. Again, the unit would be coulomb per meter, not meter square, because d is the length of the wire. Why linear charge density? Because it is the amount of charge in a small linear length, not on an area but on a length. Okay. Now I can do volume charge density also. For volume charge density, I can take another shape. What shape do you want? Oh, what did I do? Yeah. What shape do you want? Let's make a circle. Okay. Yeah. A circle full of charges. Okay. And Q is the charge. V is the volume of the sphere. Okay, this is a sphere. Okay, I can't draw a sphere, so I just put it as a circle. So if I do Q by V, and I can represent this as another alphabet sigma, coulomb divided by meter cube, because it's volume. So this is going to be equal to volume charge density. Yes. So you can see, depending on the charge distribution and depending on what you take, like area you can take, length you can take, volume you can take, depending on what you take, you can, represent different quantities like area charge density, which is the charges distributed over certain area, linear charge density, which is the charge distributed over a length, or volume charge density, which is the the charge distributed over a certain volume. So for volume charge density, it could be irregular shaped objects as well. So that is what we are going to discuss here in continuous charge distributions. Now here you can see, here it's put in a little more, complex form. So I've made it very easy for you. See, what is surface charge density? It is sigma is equal to del q by del s. So here, instead of that, I have just taken it as q by a. Okay, so you can take it as capital letter Q everywhere, because in the NCERT it's capital letter Q. You can do that as well. Now, what does it say about linear charge density? Linear charge density is Q by D, and volume charge density is Q by V. So that is the only thing mentioned here under continuous charge distribution. It just tells us that charge is distributed over a continuous surface, and depending on how you take the measurement, whether it is with respect to area, length or volume, you will have different parameters. You will get sigma, lambda or rho. Okay? Is this clear to all of you? Yes? No? Yes? No? Is it? ಈ ಸಾಲ ಕಪ್ ನಮ್ದೆ. Okay? Can you all let me know? Put some thumbs up. Good evening. Good evening. Good evening, Harihar. Yes, if this is fine, can you put some thumbs up in the chat? Yeah. I'm sorry, I have a cold. Okay. Hello, Harihar. Okay, let's move on. Is this clear to all of you? Next year, under continuous charge distribution, the next topic is, the charge distribution and electric field. So you can see there are three formulas here for electric field. E, E, yeah. So let's see how you get these formulas. Okay. So this is with respect to what we just learned on charge distribution. Okay. So for each of these, you can, let's say there's an electric field for each of these. We've seen charges. And when there are charges, there is obviously an electric field. Okay. So the electric field will always point in one particular direction as well. So what color should I take? Okay. I'll take green. So imagine for this one, all the charges, they're all, they all have an electric field dE in this direction. Okay? Yeah. Yeah. Electric field dE in some random direction. Okay, let's say it's in that direction. Now, because of so many charges, this happens. So, dq, or let's say small letter q or capital letter Q, whatever you define, you decide. Okay? So, dq is going to be equal to what? Rho into dV. How did I get that? Because Q by V is rho. So Q is rho V. So dQ is rho dV. Okay. So this is the, total charges because of this figure. Now because of the second figure, what will it be? So here also imagine there are all of these charges produce a field in one direction. And let's say it's in this direction. So dE is in this direction. So each charge produces a field in the direction of dE. Okay. So, okay. So let's say this one charge produces a field like this, like this, like this, like this. They're all in the direction of dE. So here what will dQ be? dQ will be lambda d. Okay, if this is also d, then it will be difficult. So I will do one thing. I will make this L. Okay, because I can't put dd. It does not look good. So like the length b, L. Okay. So let this length be L. So Q by L, lambda, DL. Yeah. Okay. dq is equal to lambda dl. Now, same thing here. If they all have an electric field, let's say they all have an electric field dE in one direction. So, dq will be sigma dA. Okay. Now, we know that the general formula for electric field is what? Electric field E is going to be equal to the electric field of the whole, whatever it is, the whole sheet or the whole sphere or the whole wire, is going to be integral of the electric field of a small element. See, imagine you have a big sphere. Okay. If you have a big sphere, what should I say? Yeah, you have a big sphere. You take a small area. The electric field on that small area will be equal to dE. Okay. And the electric field of the big area is going to be equal to the integral of dE, which is the integral of this small element. So let's say it's an integral of dE. Now for each case, for the sheet, for the wire, and for the sphere, you will have different values. So how do I do that? So first thing will be 1 by 4 pi epsilon naught. I'll just put it as k by r square. Now what is the charge going to be? Charge is going to be equal to, in the first case, it's going to be equal to sigma dA. Now, second case, k by r square, q is what? Q is lambda dl. In the third case, it's going to be equal to k by r square, q is going to be equal to what? Rho dv. Rho dv. So these are the different values of electric field. What is the general formula for electric field? We learned that last class. What is it going to be equal to? 1 by 4 pi epsilon naught, which is k q by r square. What is q? Q will change. So in all of these three cases, q is different because it is a continuous distribution of charges. When do we take q as q only? When it is a point charge. And if you look at my previous lectures on the same chapter, you will see that everywhere I've just taken q. Why? Because in all those cases, I am just considering a point charge. So what were the different cases that we were considering? Point charge q, another point charge q. These two are brought close. There is a force between them. You have to find out the force, the electric field, things like that. But here, what do I have? I have a surface. I have a sphere, a rectangle, or a wire, or a sheet. I have some shape which is full of charges. And I am finding the electric field because of all those charges. That is when these equations for electric field come. Okay? So that is when you get these equations in your NCERT. Okay? So these will look complicated, but in reality, it's very simple. You just need to know this much. Okay? Is that fine? Can I know in the chat? Yes? No? Hello ma'am, कैसे हो? मैं Yes? Students, if it's clear, can you put some fire in the chat? Sana, I have seen you somewhere. From this logo, you know you have seen Sana somewhere. Yes? Students, did you all mark your attendance? Please quickly go like the video, like, subscribe, and then attend the rest of the class. Okay? Can you put some fire if this much is clear? Okay, Preetu. Hi, Preetu. Preetu is the first person to put fire. Where are the others? Thanks, Kirti. Karthik. Okay. Are you all putting fire because I told you to put fire, or you've really understood something? Okay. Students, I was sick past so many days. But I didn't, your exam 3 and all is coming up. So that's why we're here to take classes for you. So please show us some love so we also get the motivation to teach. Okay. So send this to all your friends. Ask them to join class and, like, subscribe, share. So we are able to keep doing this. Okay. Yeah. Okay. So that's about this section, continuous charge distribution. Okay. It's when you have continuous charges. So these three pictures on your NCERT is the same as what we discussed. Exact same thing. Okay. Next is the very famous, the most important thing that you might all be wondering, Gauss Law. So all of you might have learned in school what Gauss Law is, but here we will learn it in a little more better manner. Okay? I won't say better, your teachers might be better, but still, I'll try. So let's say Gauss law, and First thing, let's define. Let's take a charge. Okay. Plus Q, one charge, point charge. So this charge will have a field. Okay. So wherever this charge has a field, I'll draw an imaginary surface. So we've learned in the last class that if you have a point charge, field lines always go outward. So the best shape to describe the field lines will be a circle. Students, am I still live? Because the power just switched here. Switched here. Okay, I think I'm live. Okay, thanks, Harihar. Yeah. So let's say there's a point charge. So as I said, field lines go out in all directions, isn't it? So the best surface to show the total field lines is a spherical surface, isn't it? So imagine I have some source that's producing electric field only in this direction. Then I can't put a sphere because field lines are not going to the other direction. They're only going to one direction. So a Gaussian surface is an imaginary surface. A Gaussian surface is an imaginary surface that encloses a lot of field lines. Okay? Okay. Okay. Mm, plus Q. Okay. Now, the electric field lines are always going to be outwards. Since this is a positive charge, the electric field lines are going to be outward. Yes, that is something that we have learned. So, this is the direction of electric field lines. Let's consider a small area element of the Gaussian surface. We're not going to consider the whole Gaussian, but we will consider a small element dA. Okay, let's take a small element dA, which is at a distance r from the center of the charge. Okay, now this is a closed sphere. This is a closed sphere. Yes, I mean, Gaussian can be any closed surface. Okay, it just has to be a closed surface. In our case, I'm just taking a sphere because for a point charge, the best surface to show the total charge enclosed is a sphere. Okay? So is this clear? I have a point charge. I have drawn an imaginary circular Gaussian around it. A Gaussian surface that is enclosing all the field lines. I take a small portion, a small area element, dA. Okay? Now, what I will do? Some small tiny peeny derivation. Okay. So first we will consider the flux through the area element. Flux through the area element dA. So let's say the flux is d phi. Phi always represents flux. So d phi is equal to what? E dot d A. Okay. So what is flux? Flux is the total, it is the amount of electric field passing over a certain area. Okay. Now since it's dot product, if something is like E dot or E cross, you can write it as EA cos theta, EA sin theta. You might have learned that as well. So E dot dA can be written as E dA cos theta. But you can see here, the electric, don't know what is flux, watch my previous lecture. Okay, there I've taught what flux is in detail. Basically, flux is the amount of electric field lines passing through a certain area. That is why it is E dot dA. Okay, so d phi is EdA. Now what we will do, we know the formula for electric field, so let's write that down. It is 1 by 4 pi epsilon naught q by r square into dA. Okay, this how did I get this? 1 by 4 pi epsilon naught. This is the very famous Coulomb's law. Coulomb's law. This part. Okay? Any doubts still here? Nothing. Okay. Now let's move on. So this is the flux for the small area element dA. Now, flux for the whole Gaussian, for the whole closed Gaussian surface is going to be equal to what? Integral of d phi. Yes, it's going to be the integral of d phi. Now, what will the integral of d phi be? It's going to be q by 4 pi epsilon naught r square. These are all constants. These are not going to change. So, these go out. Integral of dA. Okay. Now, what is our Gaussian? Our Gaussian is a sphere. Okay. What is the area of a sphere? It is 4 pi r square. So, integral of dA would definitely mean integral of 4 pi r square. So, this is going to be equal to q by 4 pi epsilon naught r square into 4 pi r square. Yes, dA is the small element, so the full area is going to be 4 pi r square. Now, so let's cancel the common terms. 4 pi, r square. This is going to be equal to q by epsilon naught. Okay. Now, what I have derived here is the Gauss law. So now, from whatever I have done, if you check carefully, you will see that you don't have to check carefully, you just have to see it's there. You will see that pink. Okay. What we have derived here, phi is equal to q by epsilon naught. So the total flux of field lines in a closed surface is equal to q by epsilon naught. That is our conclusion. So this is an answer to, in your exams you might have a question, derive Gauss law using Coulomb's law. This is what you should do. It's very easy if you understand, students. Only if you sit and by heart you will go wrong. But if you understand what's happening here, it's very easy. Okay? So if the question is derive Gauss law from Coulomb's law, this is what you have to do. So where is Coulomb's law here? I've already shown you. 1 by 4 pi epsilon 0 q by r square is from Coulomb's law. Okay? Is this clear to all of you? Yes. So that is what we're going to learn here. That is what is given to you in NCERT under Gauss law. So somewhere here the statement is there. Okay. Divide the sphere. Yeah, we have used Coulomb's law. Yes, I have also used Coulomb's law. Blah, blah, blah. All this we have done. Yes. All this is done. Okay. So, electric flux through a closed surface is q by epsilon naught. Okay. That is what we have found out using this circle. So you can see in this picture here, you can see here an element del S is taken. I've just taken it as dA because that is what we usually take. Okay, it's only in the NCRT where it is taken as del S. Nothing wrong in taking it as del S. Instead of dA, you can just put it as del S. Same derivation. Okay? Yes, no, I don't see. Is this much clear to all of you? Students, can you let me know if this is clear to you? Can you all put some fire in the chat if this is clear to you? Fire, fire. Ma'am and her obsessions for fire emojis. Okay, now let's look at this. See, here you have a cylinder. A cylinder is another Gaussian surface. So you can see there are field lines that are going like this. Okay, field lines like this. So, to enclose these field lines, I can't take a sphere. Right. What I should take is a cylinder such that the field lines go inside. So however your field lines are, you have to draw an appropriate surface that, that is around it. Something like that. Yeah. That would be your Gaussian surface. Okay. Yeah, this paragraph is important. The total flux through all the surfaces. So here you can see there are three. This is a cylinder. A cylinder, this has three surfaces, 1, 2, and 3. Okay. Okay. So let's say I will draw that here as well. So you saw this, right? We're going to discuss this part. Okay. This cylinder. The cylinder has three surfaces, 1, 2, and 3. Okay. Yeah. Let's draw the same thing here. I'll draw a cylinder. Okay. So the cylinder has one surface, second surface, third surface. And let's say field lines are you're all wondering, ma'am, pathetic drawing, ma'am, pathetic. I know. I can hear you from there. Let me try to make it better. I can actually use tools from the chat, but if you're watching this video recorded, please forward this part. Okay. Looks okay. You have to get the feel of the field lines passing through it. So I'm trying to make a 3D effect. Okay. Yeah. Yeah. For all of your patience, thank you. So the field lines are going in like this. Field lines are coming out like this. Okay. Now, if any field line goes in, then it's negative. If a field line moves out, it's positive. This also we have discussed. So here the field lines are moving in, so it's going to be negative. Here the field lines are moving out, so it's going to be positive. Now what about the third surface? If you look at the third surface, we know what is flux, E dot dA. So here, field lines and the area, aren't they perpendicular? Field lines are like this, third surface is like this. If they're perpendicular, the angle between them is going to be 90. So this is going to be equal to cos 90, which is going to be equal to 0, isn't it? Right? You understand? See, here we've taken d phi is equal to E dot dA. E dA cos theta. Here they were parallel, so cos theta was 1. But here you can see on the third surface for the cylinder, I don't have anything cylindrical here to show you, but let's take this. If this is the direction of electric field lines and this is area, then the angle between them is 90. So cos 90 is 0. So their flux is going to be 0. There are no field lines passing through the third surface. So along third surface, the field lines are going to be 0. So the total flux of the cylinder, which is the total number of field lines passing through in the cylinder, are going to be phi of 1, the first surface, plus phi of 2. This is the first surface, this is the second surface, plus phi of 3, which is the top surface. So phi of 3 is definitely 0. What is phi of 1 going to be equal to? E into A, minus E into A, because it is going inwards, it's always minus. Surface 2 is going to be plus EA. Surface 3 is definitely 0. So minus EA plus EA is again 0. So what is phi supposed to be? According to Gauss law, phi is supposed to be Q by epsilon naught. But there are no charges. So Q is 0. So this whole thing is 0. Okay. So you can see here, that is what we are discussing here. The total flux through the surface is phi 1 plus phi 2 plus phi 3, where phi 1 and phi 2 represent the first flux through surfaces 1 and 2, which are the circular surfaces, and phi 3 is the curved cylindrical part of the closed surface. You can see here 1, 2 and 3. So in 1, the amount of charge is minus EA, in 2 it's EA, in 3 it is 0. Okay? So yes, yeah, same thing here. Here they have taken it as S1 and S2. I always take area as A. In the textbook, it's always S. That's the only difference. Okay? Okay? Okay, not okay? Okay. All right. So that's about the cylinder. Next is the total, yeah. Let's look at the significance, the great significance of Gauss law. Okay. So there are so many significances of Gauss law. This is also a very important question. I've seen it in many past papers. Now mention the significance of Gauss law. So first one, Gauss law is true for any closed surface, no matter what its shape or size. I've already discussed this point. See, in the first example that we saw, we looked at a sphere. Gauss law was, applicable there. In the second example, we looked at a cylinder. Gauss law was applicable there as well. Now we will look at examples for sheet and different surfaces, and we will prove that Gauss law is applicable there as well. So the only condition is for Gauss law to be applicable, it has to be a closed surface. Okay? Yeah. Perfect. Second one, the term Q on the right side of Gauss law includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. Yeah. See, Gauss law phi is equal to Q by epsilon naught. That Q represents all the charges. Okay, it could be wherever in the surface. It represents all the charges. Okay. Thanks, Harihar Kumar. Harihar Kumar is a full energy supporter. Okay? Yeah. So that's the second point. Let's look at the third point. In the situation when the surface is so chosen that there are some charges inside and some outside, the electric field whose flux appears on the left side is due to all the charges both inside and outside. The term Q on the right side of Gauss law, however, represents only the total charge inside S. 1.31. Wait, 1.31 is which figure are they talking about? Because later when you open your textbook, you will be wondering, ma'am didn't explain with 1.31. So I can't see 1.31. Nine. This is 1.31. Hmm. Scrolling this irritating you, it's irritating me also. Yeah, let's not talk about, see, here the only thing you need to understand is whenever you choose a surface, there are some charges inside, some charges outside. Okay? Whatever surface you choose, there are charges inside the surface and outside the surface. The electric field is due to all the charges both inside and outside. Okay? That's all. Next, the surface that we choose for the application of Gauss law is called Gaussian surface. So in our first case, the sphere, it's called a Gaussian surface. In the second case, the cylinder, that's also called a Gaussian surface. So you may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field due to a system of discrete charges is not well defined at the location of any charge. As you go close to the charge, the field grows without any bound. However, the Gaussian surface can pass through a continuous charge distribution. Okay, so Gaussian surface should not be taken for any single charge. It has to be taken for a group of charges. So as I said, if there are lots of electric fields in that particular direction, that is where the Gaussian surface has to be. Next, Gauss law is often useful towards much easier calculation of the electrostatic field when the system has some symmetry. So it's easier to do Gauss law when it's a symmetric system, like a wire or a point charge and all. We know where the field lines are going to be, and it's going to be the same in both the directions. So it's going to be same on the left side and the right side. In those cases, it's easier to draw Gaussian surfaces. Finally, Gauss law is based on the inverse square dependence of distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from the inverse square law. Okay, so Gauss law is also based on inverse square law. Okay, yes. I'm very sorry for my cold. It was better, that's why I decided to take the class, but now it's getting worse. I'm really sorry, students. If this is, me sneezing is annoying you, I'm really sorry. Okay. Ma'am, who is your backside? Where? There's nobody behind me. Okay, let's continue. Now let's look at this question. Example 1.2. Hi, Dr. Tarun. I remember. But these are all familiar names. I've not seen anybody but my regular students. It's correct now. So before that, you saw someone behind me. Okay, Shamil saw someone behind me. Who was that? Okay. Next, yeah, question. The electric field components in figure 1.24 are Ex, Ey, Ez. Okay. Alpha is this much. Calculate the flux through the cube and the charge within the cube. Assume that A is equal to 0.1 meters. Okay. So here you have some field lines here and here. Okay. So let's say this x is equal to A. What else is given? What else is given? Okay. So this is a cube. So it has so many sides. Okay. So the flux would be there on all the sides. Let's just put it as 1. Okay. Phi 1 should be equal to phi 2 should be equal to phi 3 should be equal to phi 4. Say it should be equal to 0. Okay. Uh, Now what all surfaces I have taken? Phi 1 as phi 1 to phi 4. All the surfaces except these two. Okay, I have something here. Okay. Okay. Let's say this is a cube. So I have field lines from here to here. So they're passing straight. Okay. So except this and this, all the other surfaces, 1, 2, 3, 4. These 4 surfaces I've taken as 0. Okay. So this is phi 1, phi 2, phi 3, phi 4. All of them are 0. Okay. Agree? Now the total phi of the cube is going to be what? These two I'll take it as phi A and phi B. Phi A plus phi B plus 0 plus 0 plus 0 plus 0. Because phi 1, phi 2, phi 1, phi 2, phi 3 and phi 4, all of them are 0. Do you understand? So this is phi 1, this is phi 2, phi 3, phi 4. All of these are 0. Okay? Now let's just solve it. It's all of the things are given to you, right? The electric field is given. The electric field is how much? A alpha. Okay, so this will be the electric field is given as alpha root x. It's in I cap because it's along the x-axis. Okay. X raised to 1 by 2 is root x. That's how I got E alpha root x. Some of you like, ma'am, it's E alpha x raised to 1 by 2. How did you get alpha root x? It's just the same. So here this becomes alpha root x. I'll take it as A. Yeah, here I've already defined x is A into A square. A square is what? Area of the side. Side into side. A into A is A square. So I took x as A so that I can equate. Okay? Yeah. Plus alpha square root of 2A into A square. Okay, how did I get that here? So here I take x as So here I will take x as 2a. So E would be alpha root of 2a. And then if you just equate it, you just have to do the math. So it will be alpha you take outside. So once you take alpha outside and then you have a square, you do the math, you will get the answer. Yeah, you will get something like this. Alpha a raised to 5 by 2 square root of 2 minus 1. The value of alpha, the value of a is all given. You will get 1.015. Okay, now you just have to find out, you just have to use Gauss law to find out the total charge. Total charge will be what? Alpha would be Q by epsilon naught. You have you have phi. You can just do this. You have phi, you have epsilon naught. You can easily find out Q. It's an easy question. Okay? Yes. Let's move on to the next question. Okay. Yeah. Is this clear to all of you? Okay, carry on. Is that to me? Okay. Students, just excuse me for a minute. You can read the question. I will be back. Just a second. Yes. Yeah. Sorry for that. Okay. So the question is, an electric field is uniform and in the positive x direction for positive x and uniform with the same magnitude but in negative x direction for negative x. Okay. It is given that E is equal to 200 I cap. Okay. E is equal to minus 200 I cap for x less than 0. At right circular cylinder of length 20 centimeter, radius 5 centimeter, center. Okay. So we have to find out the net outward flux, flux through the side of the cylinder, net outward flux through the cylinder, net charge inside the cylinder. Okay. Okay, let's do it. Are you all ready to do it? First thing, let's define the figure. So how will the figure, it's already given that it's going to be a cylinder. So let's draw a cylinder. Again, getting back to my poor skills. Okay, let me try something else. Let me try putting. Ah, that worked. Okay. Wow, I was successful in drawing a good cylinder. I mean, yeah. Okay, so this is a cylinder, and then there's a surface that's also given to you in the question. The surface, what shape should I take? Okay, something like this. What am I doing? Yeah. Okay, so this is the surface. And then let's draw the axis. Perfect. Yeah, so this is the axis. So this is x, this is y, this is z. Okay, now this much of things are given to you. Now what else is given at a yellow color? Okay, green is also fine. Yeah, so r is equal to 5 centimeter. That's given to you. Now, along this surface, we know that the area is perpendicular. So, whatever field lines are there, they're going to come out of this side, come out of this side as well. Why is it coming out of both? Because it's coming from a sheet, from the center. Isn't it? I think I should have. Okay, it's okay. So, this is given to you in the question. How much is it? I cap? No, 200, right? Yeah. So, this is 200 newtons per coulomb. Here also it's 200 newtons per coulomb. And yeah, and this whole length is 20 centimeter, the length of the cylinder. That's also given to you in the question. Nothing to brainstorm here. So this much is given to you in the question. So to solve it, first thing, let's find out the flux on the curved surface. On the curved surface, it's obviously 90-degree. So the electric field is perpendicular to area, so it's going to be 0. Cos 90 is 0. Then let's find out flux on surface number 1, which is a, what do I say? The flat surface. Okay? Surface number 1. So here, field lines are coming out, so they're definitely positive out, so it's positive. So this is going to be equal to EA cos 0, which is 200 into, what is the area of a sphere? Pi r square. So the radius is, excuse me, just a second. Okay. So 200 into pi r square. The radius r is 5 centimeters. So when you convert it into meters, it becomes 0.05 meters. So this is going to be equal to 200 into 3.14 into 0.05. You can just do the math, you'll get the answer. Okay. Now, the total flux phi net is what? There are two surfaces, surface 1, surface 2. So phi of 1 plus phi of 2. And yeah, obviously phi curved, which is 0, but still, let's just maintain the equation. Let's put all the terms. And then, yeah, so since in both the cases the field lines are moving outwards, they're both positive, they're both going to be the same. So this is going to be equal to 2 phi 1 plus phi curved. Now I can put it as 0. Why should I write it as phi curved? I'm just going to put this as 0. So this is now going to be equal to, can you see? I hope you can see. Yeah. Yeah, you can see, I think. Yeah, so this is 2 into 200 into pi into 0.05 square. That will be a total flux. Now, if you want to find out Q, what is the formula? Epsilon naught times flux, right? Yeah, phi is Q by epsilon. Q is epsilon naught times phi. And then you just have to multiply whatever value of phi you get. So this is basically going to be equal to 8.85 into 10 raised to minus 12 into phi, which is this. That's all. See, the question looks, like, something, it looks like rocket science, but it is not. Okay? It is not that difficult. Is this fine? The chat is not loading. Where is the chat? Okay. Okay. Yes, if this is okay, can you all put some fire in the chat quickly, students? Quickly put some fire. Okay. Okay. Yes. Next is the most important applications of Gauss law. Okay. Thanks, Preetu. So there are several applications of Gauss law that we will learn. I mean, that are there. But here in this chapter, we will learn three main applications of Gauss law. Okay. So first thing is the first application, field due to infinitely long, straight, uniformly charged wire. So this is a figure. If you've already learned this in school, this would be the figure that you've learned. So should we use the same? Should we draw again? Based on my skills, you would say, ma'am, use this, no? Okay, I will use this figure. Okay, so there's a long rod, a long wire that is full of charges, and each of these charges at a distance r. Okay, so to accommodate all of these charges, we make a cylindrical Gaussian surface. I can't put a sphere here because, see, if I put a sphere here, the charges are not going to be equally spaced with respect to every point on the sphere. How do I say? See, if I have a charge like this and I put a sphere here, see, this part of the sphere is touching. This part is far away, but it's not symmetrical. So for a straight wire, only if it's a cylinder, it's symmetrical. Right? The charges have the same effect at every point on the cylinder. Okay, so it is at a distance r, and let's say the electric field is in this direction. Area is also in the same parallel direction. Okay. What else? Yeah, this is at a length L. L is the length of the Gaussian surface. Now, what we will do, first thing we'll find out the total flux of the cylinder. So the total flux of the cylinder is going to be equal to Q by epsilon naught. Without doing anything, how did I get that? The very famous Gauss law. What does Gauss law say? The total flux enclosed in a Gaussian surface is always Q by epsilon naught. Yeah? Yeah. Okay. So now, here there are different surfaces for a cylinder. It has two top surfaces and it has a curved surface. But on the two top surfaces, would there be any field line passing through? See, if you have, we'll take this itself. If you have an area like this, there are field lines passing through here. So there's a flux here. But there are field lines passing through here. But it's not going to touch or cross. It's just passing above. So it has no flux there. Flux is only when it passes through a certain area. So on the top, you can see field lines just pass through like this. It is not passing through the area, it's passing on top. So there is no flux on these two surfaces. Okay. So for the cylinder, you don't have to consider the top and bottom circular surfaces because there are no field lines passing through there. There is no flux there. So for a cylinder, for a straight current carrying wire like this, okay, this is infinite, okay, this is forever. The length of the wire is forever. For a wire like that, you only need to consider the spherical part, the cylinder. So you can see in different cases it's different. In the previous case, we looked at only the two sides because there the spherical part was perpendicular. Here you only look at the spherical part. Okay, so you have to be careful when you do. You don't have to be careful, you just have to understand. Okay, so that two surfaces, top, no flux. Bottom, no flux. It's like, this is the surface, the field lines go like this. Okay, so now let's do the math. What will we do? So this is a wire. We've already defined for a wire. So yeah, here for a wire, linear charge density is what? Q by L. So we will use something here. We will use the same thing here. So whatever you learned is not to forget, is to apply somewhere else. So let's do that. So for a sphere, we learned that Q is lambda, right? Lambda was lambda was Q by L. Q by L. Let's just put that there. Okay, now let's start. So, the total flux is always, okay, I'll use a different color. The total flux is always EDA. All of you agree? And EDA is always Q by epsilon naught. Gauss law. Yes, this much everybody agrees with me. So this is going to be EDA cos theta, which is cos 0, 1. So I will just put it as E dot dA will be, okay, EDA cos 0. And what is Q going to be equal to? Lambda into L. Lambda L. Lambda into L EDA cos 0 by epsilon naught. Now this is going to be equal to E is a constant, dA, which is lambda L by epsilon naught. Okay, do you agree this much? How did I write Q as lambda L? Surface charge density, linear charge density. Okay, now what I will do, what is the area? Area of a cylinder is 2 pi RH. So E times, so dA is a small element of the cylinder. So integral of dA is the area of the whole cylinder, which is 2 pi r into length of the cylinder is L, right? Yeah, it's L. 2 pi r L, which is lambda L by epsilon naught. Now from this you can write E is equal to L and L will cancel. Lambda divided by 2 pi epsilon naught r, which is 2. What I can do is I can write it as 2 divided by 4 pi epsilon naught lambda by r. Lambda by r looks good. Now 1 by 4 pi epsilon naught is k. So this becomes 2k lambda by r. So this is the formula that you have here. This one. This formula. Okay? Yeah. So field due to an infinitely long straight uniform wire is as simple as that. This is all that you need to do. Okay? So what all do you need to know? The top and bottom surfaces have no flux. So you only consider the spherical surface. Spherical surface is always equal to Q by epsilon naught, which is Ohm's law. Gauss theorem. Yeah, Gauss theorem. Okay. Now what is Q? Lambda L. For that it is very important to learn all those three conditions that I taught you. So now you know how to relate all this. So here you have multiple charges. So when you have multiple charges, you have to consider those three cases. Okay? And then just do the math. Okay? I hope this is clear to all of you. Yes, no. Okay? Same thing is given to you in your NCERT. Next one is field due to uniformly charged infinite plane sheet. Okay, so here let me draw a simplified figure. So you have a sheet that's given to you. Okay, there is a sheet. Okay, so even on the sheet, what we do is we define a something like this. Okay, so this is a charge sheet. So because it's a charge sheet, it will have field in both the directions. So it will have field in this direction and this direction because it is a charge sheet. So it keeps, emitting charges. It's a Gaussian surface. It's a uniform surface. So sigma is equal to Q by area. Yeah. So charge is sigma A. For a sheet also we have discussed in the first three cases, remember? Sheet also we have discussed. Now we will do the same thing. Find out the total flux. Very easy. The total flux is always Q by epsilon naught. Now, here the total flux is because of these two surfaces, not this surface. Why? Charged field lines are perpendicular here. So, it is because of this is surface 1, surface 2, surface 3. So, phi is equal to phi 1 plus phi 2 plus phi 3. But phi 3 is 0 because it's cos 90. Okay? Now, what will phi 1 and phi 2 be? It will be EA. Both are positive because both are going out. Anytime field line is moving out, it's positive. Field line moving in, it's negative. These are all tricks and tips that you should remember. Okay? Yeah, and this is going to be equal to Q by epsilon naught. What is Q? We already learned sigma A. So sigma A by epsilon naught. Now you have 2EA is equal to sigma A by epsilon naught. A and A cancels. So 2E is equal to sigma by epsilon naught. So E is going to be equal to sigma by 2 epsilon naught. This is the electric field for a sheet. Okay, yeah, you can quickly look at it. Very easy. You only have to understand the concept here. You have a sheet. Since it's a sheet, it emits electric field in both the directions. So it's both outwards. So it's going to be EA EA. And since it's a Gaussian surface, the total electric flux should always be Q by epsilon naught. Now, what is the value of Q? Here you are considering area. So you have to take sigma A. Okay? Yes. Okay. So that's how you get this formula. Now, the third application is field due to uniformly charged thin spherical shell. Okay? So here you're actually going to look at two different cases. The field lines due to points inside and outside. 1 second, I'm not able to see the chart. Okay, so this is the last application. We're done after we finish this application. So let's look at the figure first. So this is electric field due to spherical shell. So let's say you have a point, okay, and shapes sphere. Okay, so this is at a radius of r. Okay, now I'll put one more sphere. This is where the charges are. Okay, now from the center, this distance is capital letter R. Okay, this is fine. Now, what we can do is Control C, Control V. Perfect. Yeah. Same charged spherical shell. And then this is at a distance r, that is the same. Now we are going to consider the Gaussian surface outside. I'll explain this in detail. Just a second, let me finish drawing it. Yeah. So this distance is r. Okay. Okay. So this is the Gaussian surface is inside. So r is less than capital R, right? R is less than capital R. Okay. Now this is outside. So R is greater than R. Okay. Yeah, that much is fine, I think. So let's do these simultaneously. So phi of the sphere is what? Q by epsilon naught. You might not be able to see this because of my head. That's the problem, Limitations of not having a big screen. I'm already covering the picture. I'll write it here then. Okay. So here also, phi of sphere is Q by epsilon naught. Okay. So in both the cases, it is Q by epsilon naught. All of you agree? Yeah. Now, what I'll do? Integral of E dot dA. Yeah. But, mhm. Are there any charges on the pink sphere? There are no charges on the pink sphere. So this is going to be equal to 0 by epsilon naught. Isn't it? Because I am considering a Gaussian surface inside, the charges. So since it's inside, I'm looking at the pink sphere. So the pink sphere has no charge. You can see the yellow crosses are the charges. So Q is 0. So this becomes 0 by epsilon naught. So dA is what? E into integral of dA is 4 pi small r square. Why small r? I'm looking at the pink Gaussian surface. This would be 0 by epsilon naught, which is 0. See, 4 pi r square can definitely not be 0. So what has to be 0? E has to be 0, which means no field inside. Okay, is this clear? Now let's do the same thing for outside. Yeah, for outside, what happens? Again, integral E dot dA is equal to Q by epsilon naught. All this is fine. So E 4 pi, again small r square. Why small r square itself? Because I'm taking the outer sphere, yellow sphere. I'm looking at Gaussian surfaces outside and inside a conductor. Okay? Yeah, E 4 pi r square will be Q by epsilon naught. There are charges here, so I'm putting it as Q. So E is going to be equal to 1 by 4 pi epsilon naught Q by R square. So this is similar to electric field of a point charge. So if I take a Gaussian surface outside a conductor, it's going to give me a formula similar to electric field. This is just like a point charge. So this is a short and quick derivation for inside the sphere and outside the sphere. Okay? Is it visible? Yeah? Okay? That's all. You see, all of this is very easy. The only thing is you need to know the concept. Okay? So I should have used same color. Yeah, I've used same color. In the first case, I'm finding out the flux on the pink sphere. In the second case, I'm finding out the flux on the yellow sphere. That's all. Okay? Yes. So that's all. That's the, applications. The field due to spherical shell. Now there's one more question. Okay, one last question and chapter 1 is done. Let's solve that also. So chapter 1 NCRT I've done fully. Every exercise question, everything in the textbook I've explained in the last 3 sections. So let's look at this question as well. Why should we? Okay. Yeah. An early model for an atom considered is to have a positively charged point nucleus of charge Ze surrounded by a uniform density of negative charge up to a radius r. The atom as a whole is neutral. For this model, what is the electric field at a distance r from the nucleus? Okay. So this is like, you have a central positive charge and then you have negative charges floating around it. Like a flower, we see the sunflower as a black central part and yellow all around it. Similarly, this positive in the center like a nucleus, not a nucleus, just like a nucleus, and the negative charges all around. So let's draw a figure. So there's a positive, let's put it as ZE, and then around it is a negative minus ZE. Okay. Now, yeah. Okay, yeah. Now what we'll do, we will take a Gaussian surface outside this. So since this is a circle, the Gaussian surface also has to be a circle. Yeah. So from here till here, it's going to be R. Okay. And this is the Gaussian surface. Alright, Gaussian surface is at a radius r. So let's do it. Phi is definitely going to be equal to q by epsilon naught. Gauss law. Phi is what? Integral E dot dA. So sometimes you have to write it as closed integral. Okay, I write this line and put a circle on it. That means closed integral. It is the integral of a closed surface. So this is going to be equal to Q. What is Q? Here, what is the charge? It's going to be plus ZE and minus ZE, right? Those are the two charges. So can't I just write it as ZE minus ZE? Yes, divided by epsilon naught. So in every question, the most important thing is you need to know what the charge is and then you need to know what the area is. Then it's all very easy. Now, E dot dA is E dA cos 0, which is ZE minus ZE 0 by epsilon naught. So E into 4 pi r square is equal to 0. So E definitely has to be 0. Right? 4 pi r square cannot be 0. So E has to be 0. Yeah. So this is for a Gaussian surface outside. Now we'll do the same thing for a Gaussian surface inside. So let me see if I can copy paste. Okay, I could. Control C, Control V. Okay. Now we should put a Gaussian surface inside. Let's use the same blue. Shapes, circle. Yeah. The pink also should be a good sphere, but I'm sorry. Okay. So this is the new Gaussian surface inside. Okay. So here we have to find out the charge, right? First step is always to find out the charge. So since it's a sphere, what we should do is we should do charge by volume. So charge by volume will be what? Charge is ZE, volume is 4 by 3 pi a cube. So this radius, I'll just put it as A. Okay? Because this inside one is going to be R. So that let me put this as A. Now this is going to be equal to the charge on the surface, which I don't know. So I'll just put it as Q minus divided by 4 by 3 pi r cube. This is the charge on the Gaussian surface, which I don't know. So that's why I'm going to put it as Q minus. So from this, I will equate it. I will get Q minus is equal to ZE by A cube R. Okay. Now, the rest is very easy. What is total Q? Total Q is, no, before that, I need to write something to substitute Q. Let's write that as well. The same old usual steps. What are they? E integral dA is equal to Q by epsilon naught. So this is E into 4 pi r square is equal to, this is going to be Q, so ZE A cube R cube epsilon naught. Okay, so this I can write it as ZE by epsilon naught. I can write it as 1 minus R cube by A cube. I just took ZE outside. Okay. So this will now become E is equal to 1 by 4 pi epsilon naught ZE by R square 1 minus R cube by A cube. I think this much is enough. Is that the final answer here? Yes, same thing. Okay. So this is what you should do for a a Gaussian surface inside and outside. Is this clear to all of you? Okay. So that is the end of unit 1. We have discussed all the questions, everything. So this is just a summary and then points to ponder, all that you can do. And then there's an exercise also which you can solve and try out. Okay. So chapter 1 is successfully done. So all those who have attended all the 3 lectures, part 1, part 2 and part 3, please let me know in the comments if you've enjoyed this, and if you want more such videos for more such chapters, you can just let me know. I will be happy to do it, but only if you guys support us by letting us know what you want in the comments, we can keep doing more chapters. Okay? So thank you all for your patience. Thank you all for being present in class. Yeah? Yes, Sana, you can go have dinner. Class is done. Okay? Yeah. Okay. Thank you so much, students. See you all with another video tomorrow. Okay? Bye-bye. So if any of your friends are preparing for exam 3, ask them to come join Vedantu Karnataka. Okay? So from tomorrow, we will be having full-fledged classes for physics on exam 3. Okay?